to ElixirZone. Today we will build out a module and evolve it using types and specs, property-based testing, and a variety of other things. It'll be a little more involved than some of the toy examples you see in the documentation, and give you a little more sense of how you might use Elixir in the real world. Reminder that all of the code that I'm going to present today is available to you as live books inside this ElixirZone repository on GitHub. Today's episode is Elixir 102, and so all the live books are here. The main thing we'll do is we'll start with the first iteration of myval and work through the seventh and last iteration of myval. But before we do that, I'm going to go into Elixir 101 extras, which is sort of, I had a few extra, it's sort of bonus material for Elixir 101, the first presentation I gave on Elixir. Had some additional thoughts. I want to clarify a few things, go a little deeper. So let's start there. First, I want to point out, I mentioned that some functions are automatically available to you when you're writing Elixir. Normally you have to preface everything with the module name and then the function, separating them with a period. But that's not always the case. There are some functions that are automatically available to you wherever you are in Elixir. And I sort of waved my hands and said, well, they're in the kernel module. And while many of them are, not all of them are, there's also something called Kernel.SpecialForms. The way namespaces work in Elixir, the dot here is not any sort of magical thing that guarantees that it's in a certain hierarchy of file structure or a directory structure or anything. The name is the name. So Kernel.SpecialForms is just an atom, and kernel is an atom. And they're both names of a specific module, and there's no intrinsic relation between the two. I'm not sure why they're in these functions, and it's not just functions, it's macros as well, are in two different modules, but they are. And that matters to you in part because when you look for documentation on various functions that you might want to use, these are two places that you might not think of looking, but are actually quite important to know about, and that's why I want to highlight them here. So again, Elixir has fabulous documentation, Hexdocs.pm. Some wonderful people built that out so that we can have great documentation. And this is a screenshot from the kernel module. Again, most everything in kernel is automatically available to us, so you don't have to say kernel.isNumber. The isNumber function is just available to you wherever you are. So without the use of the kernel.prefix, because they're automatically imported. Similarly, there's a Kernel.SpecialForms, and I'm not completely clear on the distinction between the two. A module is in part a bucket for functions. You can put functions into various buckets. Clarity and ease of finding those functions are the main reason that you would put a function in one module versus another. There are other reasons as well, but there's a special forms bucket that seems to be specific to the building of Elixir. I suspect that the stuff in kernel is not necessarily specific to Elixir. So some of these functions in kernel I think may be sort of like Elixir syntax over Erlang functions that you could call through Erlang, but they've made it easy to call the same things through Elixir, but I'm not completely clear on the difference between these two things. But there are two different modules, and you'll notice that there are a lot of functions, things like exponentials, notation. There's a lot of the match. This is a match operator. A lot of operators, a lot of functions are in these two modules, and so it's good to know about them. And the documentation is so good that I encourage you to just go to these two files on Hexdocs and look through all the functions and get a sense of what they do, what's available to you. That said, I want to dig into structs a bit more. We covered maps and structs in Elixir 101. I want to go slightly deeper now because I had a few additional thoughts. I sort of said at one point that structs are a special form of map, but there's a key difference, and it's confusing. They're very similar, but they're not the same thing. So here it says underneath, and again, this is in the And you might not think to look for documentation on maps or structs inside Kernel.SpecialForms, but that's where some of the documentation lives, because there's a function that's defined there. And so it's good to know that this documentation is here. So underneath a struct is just a map with a special additional key, the struct key, pointing, in this case, to the user module. So the thing on the right here is the struct. And so this would be an ordinary map with the keys name and age as atoms. But in this case, there's this additional special key which has the name of : double underscore struct double underscore. And so this defines it as a struct. But this is a map, but it's also a struct. But there's a few things you can't do to a struct that you can do to a map. But many of the things you can do to a map, you can do to a struct. And so I want to clarify that. So the main difference, I think we'll see down here. So here it says, although structs are maps, by default, structs do not implement any of the protocols implemented for maps. So any map functions, anything in the map module, you should be able to use on a struct. But maps also implement a few protocols, and those are not implemented for structs. And that can trip you up. You can think, why does this function not work, or as I expected it to? And it's because although structs are maps, they're not exactly maps. They're treated slightly differently because the protocols that you typically get with maps are not available to structs. So again, the right-hand side here is sort of the spelled out struct, and the left-hand side here is an equivalent version, if depending on how you define user. If the default were John, So the struct fields can be given when building a struct. So you can pass it. You can just say on the left-hand side here, you can say user, and it'll build with the default values. Or you can specify values. So you're sort of kind of passing a map into this. I guess in this case, it could be a keyword list or a map. And then so we're going to talk today a bit more about pattern matching, because I didn't go as deep on pattern matching as I wanted to as well. So once you have a user defined, you can pattern match. So this single equal, please notice the difference here. Double equals is basically saying, okay, is the left-hand side equal to the right-hand side? And the value of this would be true or false, depending. If the default user name were Pat, then this would be false, because the right-hand side user struct would be different from the left-hand side user struct. But if these were the default values, then these would be equivalent, and this would return true. That's a double equal sign is basically saying, are these things equal? The single equal sign is not an assignment operator, and it's not generating a Boolean. What it's doing is pattern matching. So it's saying, okay, take the thing on the right and try to match it to the thing on the left-hand side. And so if this user is a user struct, and if it has an age key, then this will match, and the value of the age variable will be set to whatever the value of the age key is in the user on the right hand side. So that's a way to pattern matching, and then you're setting this age variable equal to the value of the age key in the user struct on the right. And you can update, just like you can update a map, you can specify that user here has to be a user struct. And this sort of vertical bar is saying, okay, take the user who needs to be a user struct, and then set or change the value of age to be equal to 28. So it could have been 32, it could have been 28, it could have been nil, it could have been whatever. But what you're doing is you're returning a new user struct based on the user struct user, but with the age value set to 28. And please also note that Elixir is immutable, so this does not change this user variable. The user variable stays the same, but the value of this whole this whole operation is a new user struct, and that new user struct could be assigned to another variable, user2 perhaps, or you could reassign it to user. So you could say user equals user, vertical bar, age 28. And that would update the reference of user to point at this newly generated user struct. It wouldn't wipe out if anyone was already holding on to a reference to user, it would not change the data that they were seeing. But you, in your local context, would be redefining the value of user to point at the newly generated user struct. So structs are maps, but they don't have access to map protocols that map implements. There's pattern matching. Pattern matching on the struct name. So you can. This is really cool. You can pattern match on the struct name. So if user here is a let's say player, then if you said this is because it's a single equals sign, you're pattern matching. You're saying so the thing on the right, I want it to match against a struct, and since I'm using lowercase struct name here, whatever the value of the struct key inside the user struct is, it will pattern match against struct name. So if user here is a user struct, then struct name will be user. If user here is a player, then struct name would say player. So whatever type, this is basically extracting out the type of struct from whatever you have on the right hand side here, assuming it's a struct. If it's not a struct, this won't pattern match and you'll get a match error, as I'll show you in a few minutes. But this is a way to pattern match out the type of struct that you have. You take the actual struct, put it on the right, and on the left-hand side you use a notation like this. And it doesn't have to say struct name. This is arbitrary. It could be A, it could be struct type, whatever you want to call it. But it will create a new value, and it will a new variable, and it will have assigned to it the value of whatever type of struct the thing on the right was. Similarly, you can also, if you don't care about what the struct type is, and you just want to confirm that user is a struct, you can do this, and this will return the user if it is a struct, and it will generate a match error if user is not a struct, because the underscore operator is saying I don't care what it is, don't assign it to anything, but this shape for pattern matching purposes is a way to pattern match a struct. And you could say underscore something. You could say struct type, but it wouldn't matter. Anytime the first letter of the first character in a variable name is underscore, then it'll just throw away. It'll say, okay, I know you're expecting something to be here, but you're going to ignore what it is. You don't want me to save that, so you can use it later. So let's look at a couple of quick examples. So here we're going to define a user struct with def struct like we did last time. Here it's just super dead simple. There's just a name, so there's going to be one key of name, and we can create a struct like this, and since we didn't define a default value, it's just going to assign nil. Here we're doing the same thing, but we're going to say, okay, the name is John. But here what we're going to do is we're going to take this new user struct that we have, and then we're going to turn it into a map. So there's a function in the map module called fromStruct, and that will take a struct and return a map. So here it's stripped off. You'll notice there's no longer anything after the %, because we've basically turned the struct into a map. This is just, I don't even know why I have this twice. It looks like I have the same thing twice. I was probably trying to do that. But here we can go take, so this is what we just saw, and now we're going to just go the opposite direction. We're going to take that. Once we get we have a struct, then we turn it into a map, and we can turn it back into a struct. So in this case, I'm going to say, okay, take the map from the previous step in the pipeline, and then we're going to call this struct function, which is what you'll notice when I highlight it, when I'm just hovering over this, and you can see the documentation pop up, which is really cool. Thank you, whoever is responsible for developing this. Is amazing. And you can even go back up and see more. You can see all the details. So this is the struct function is in the kernel module, but you don't have to say kernel because it's automatically included. So, and it takes a struct, and it takes a list of a keyword list of fields, or I think a map, but the default is an empty list if you don't pass anything. So here what we're doing is we're taking our map that we generated from here and we're passing it in and we're creating a new user struct. And so now we're back to, you'll see the user part is there. So we're back, we turned the map back into a struct. An identical way to do this with fewer characters. This is identical to the line above. This is just basically saying, okay, form a user struct with the map that I'm passing in. I just talked about pattern matching. Just to be totally clear, I want to go over an example here. So equal sign in most languages is an assignment operator. In Elixir, so you can say x equals x plus 1. In Elixir, that doesn't make any sense. X equals x plus 1 will not work in Elixir. Actually, let's even do that. I'll see. Actually, we do y equals y plus. Let's say y equals 3. It'll let me do that. And then if I say y equals y plus 1, it's going to yell at me. No, did not yell at me. Oh, you know why? So this is something you probably want to avoid doing. But this actually works because Elixir allows you to redefine, to rebind variables is what it's called. So on the right hand, what it's doing is it's evaluating the right hand side. So it's saying, okay, I know that y is equal to 3, and I'm going to add 1 to it. So I'm going to get 4. So the value of the right hand side here is 4. And then it's going to rebind the variable y to the value of 4. So this is rebinding. In Erlang, you can't rebind variables. This would blow up totally in Elixir. In Erlang, in Elixir, you're allowed to rebind variables, but it's something you probably don't want to do. And if you want to avoid doing that, this is what you need to do. You need to use this operator here. So if I say y equals, in this case, so we know y is equal to 4. So if I say y, actually, if I say y is equal to 4, that, well, whatever I say. So if I say y is equal to 4, it's gonna work. But if I say y is equal to 5, this will blow up because this is saying I want to use the current actual value of y here. And so what this is, and since we know that the actual value of y right now is 4, what this is going to try to do is match the value on the right hand side, which is 5, to the value on the left hand side, which is 4. And this will blow up at us. Yeah, so now we're getting a match error. No match of right hand side value 5. So it's expected, because I'm using this operator, I'm saying don't rebind the value of y. Don't rebind the variable y to a new value. Only successfully pattern match if the value of y is equal to whatever is on the right hand side. So let me show again. So if let's try a different variable. If I say z is equal to 5, there's no problem doing that because I haven't defined what z is yet. But now z is 5, and if I say hat z is equal to 5, this will pass. There we go. But if I say hat z is equal to 6, it's going to blow up with this match error. So the pattern matching, so now let's look at a little more complicated examples. So here I'm going to find x is equal to, and I just used x above, so no, that's why I didn't use x, I used y, so I wouldn't screw this up. So x is equal to this map. So the map has 3 keys, 1, 2, and 3. Usually you don't want to use numbers as your keys for a map, but there's nothing preventing you from doing so. So that's why I want to show you a different version. With this, you can say, actually, I think you can say x of 1. Does this work? Yes. Okay. So you can get the value out that, get the value of the map out from the map that way. Another way to do it is use a map function. Is it get or fetch? Let me see. Actually, let me see if the documentation pops up, because then I can look at this. This is so cool. There's a get and a fetch. I always forget. So if we try to get the value of a out of an empty map, we're going to get nil. If we try to get the value of a out of a map that has a key of a, we will get the value. So let's try that. So map get. So in this case, the map that we have is called x, and the value that we want to get is, let's say, 2. So we should see b. So this is using the map module's get function to extract the value out. So now that we see a bit more how maps work, so these 4 examples will all pass. None of them is going to blow up. So on the left and right hand sides of this first equation, or this pattern match, we have identical maps, so they work. On the second pattern match, you'll see here's the equal sign. Everything on the right hand side is present on the left hand side, but there is a value on the right hand side that's not on the left hand side. That's okay, because the way pattern matching works is it says, okay, is everything on the left hand side present and equal to the value on the left hand side? Sorry, everything on the right hand side, if it exists on the left hand side, is it present and equal on the right hand side? So 1 is A, 1 is A, and 2 is B, 2 is B. The fact that we didn't specify 3 here is not a problem, because we're not trying to pattern match the whole thing. We're just saying we're saying that anything on the left hand side has to be present on the right hand side and have the same value. So certainly here's another example. Here we're just pattern matching that C is equal to, sorry, 3 points to C, which it does on the right hand side. We can even pattern match an empty map against another map. This is just basically saying, is the thing on the right hand side a map? So all of these pass. What you can't do is the opposite. You can't have more stuff on the left hand side than the right hand side. So let's show that this blows up. So here the left and right hand side both have 1 and 2 equal to the same value, A and B. But on the left hand side, there's a 3 pointing to C, and it's not on the right hand side. So you can't pattern match everything on the left hand side against stuff that's on the right hand side. This will fail because it's missing one of the things. And probably the simplest example to see that with is the bottom one. Whereas, so up here, we successfully pattern matched an empty list on the left to, sorry, an empty map to a map with keys and values. But when we try to do the opposite, where you try to pattern match an empty list against a list that has an empty map against a map that has keys and values on the left hand side, that will fail because it can't find this on the right hand side. And then one of the main reasons you want to do pattern matching is to extract values out of like nested data structures, for example. So here on the right hand side we have 1, 2, and 3 as the keys, and let's say we want to get the value of the associated with the key 3. This is the way we would pattern match it. We would say, okay, so I expect the thing on the right to have a key of 3 and a value, and I want to assign whatever that value is to a new variable called value of 3. And then print out return the value of 3, and we get C. So that's pattern matching. Just be aware that the single equal sign is a pattern match operator, or a match operator it's typically called. The double equals, which we saw, where did we see it? Somewhere we saw double equals. I'm not finding it now, but that is going to give you a Boolean, basically saying is the right hand side and the left hand side values identical. So we've just seen the value of documentation and how it can be all this beautiful and rich. It can be a little tricky to find certain things. So you want to become comfortable surfing through the documentation because sometimes functions and macros can live in nooks and crannies where you're not expecting them. So I showed in the kernel module earlier, the struct has valuable information about structs. This is an example straight out of the documentation, but if you're not looking in the kernel module, you wouldn't see this useful documentation. So it's good to play around with the documentation. I've just started using this thing called Dash, which is not free. I have no association with them. I'm not making any money off this, but I just paid them $30 because they make it really easy to surf through the documentation. It's only for Macs. This is something I've used on Linux machines before, and it's completely free. It's not as good. One of the reasons why I'm in love with Dash right now is because it not only has the Elixir docs, but also has Erlang docs, and is making it much easier to surf through the Erlang docs than, you can get the Erlang docs online and search for them on Google, but they tend to be really large and it's kind of hard to find what you're looking for it's now a lot easier at least through Dash, to find targeted information within the Erlang docs. But it also covers hex packages like Phoenix and all the other libraries that you'd want to pull in that have Hexdocs documentation. So I'm loving this, and I'll show you an example in a little bit. Actually, here we go. So the Elixir and Erlang docs are now searchable. This is sort of what the GUI looks like of Dash, and you'll see this little thing pop. This is a search window, and if I type ERL:, it will scope my search to just Erlang documentation, which I've done here, and I search for the phrase Erlang. I was looking for the Erlang module and found it right away by typing ERL:, and then Erlang. It gave me the main Erlang module within the Erlang documentation. Similarly, if you type Elixir:, you'll get your search query will be scoped to just Elixir documentation. One of the reasons I want to show you the Erlang module is because there are tons and tons of functions in Erlang that you can use. You can call any of this from within Elixir. The notation's a little different. Someday in the future, I will go into the differences in the Erlang and Elixir notation and how you can call Erlang functions from within Elixir. I won't go into that now, but it's great to know that it's easy to surf the documentation of Erlang now and find some cool stuff. For example, there's something, I've used this in the past, it's really useful. So there's something called binary to term and term to binary, and these functions allow you to take basically Elixir data structures or Erlang data structures of any kind and serialize them to binary formats that you can save to a database or to a file, and then you could later marshal them out of the database or the file back into Elixir terms. So term is an Elixir Erlang term, meaning any Elixir data structure or Erlang data structure. So, and binary is sort of, in the early days of Erlang, they didn't have strings, and so this is sort of saying a way to convert strings to Erlang data structures. And term to binary is it's an obscure way to say turning Elixir data structures back into strings that you could serialize to a database or a file or something. And I've made use of this. It's really cool, but it's nice to be able to so quickly find documentation and surf through the various things and get a sense of what's available to you in Erlang, not just the stuff that you know about in Elixir. And as I was doing that, I discovered another cool thing today called universaltime. So if I tested this out and it works. So if you say Erlang universaltime, the notation's a little different in Elixir. You have to prefix the module with a colon, and then you replace the colon here with a dot. But it'll work if you do that. If you put a colon here and a dot here, it will work. And you don't need the period because that's an Erlang only thing. In Elixir, you don't do that. But if you say :Erlang dot universaltime, it will return you this data structure, which obviously is the year, month, and day, the hour, minute, and second, and this is based on UTC. And then you can take that the value that this data structure here and pass it through universal time to local time, and it should return you your local time, and it did for me. It knew that I was in New York. It looks at the underlying operating system, in my case the Mac, but it worked. So I got the local time and date through this function. So, and I didn't know this existed, but it's really easy to surf the documentation with this dash, and so I found that today. That was cool. But this is the thing that blows my mind, is that you can also download hex documentation. Any library like Phoenix or Ecto or whatever you want that's available in Hexdocs, you can download into Dash and surf that. It indexes it and lets you search it as well. So that's what I'm doing here. So if you type HEX:, it will scope your query to just hex documentation. And then in this case, I searched for Phoenix, and I clicked on it. It gave me a list of like high-level topic things, and I said guides, and then it dropped down and there's a list of all the guides that are available. But you can surf all kinds of different things within the Phoenix or any other Hexdocs documentation. None of this would be possible, especially like the Erlang documentation, without all the tremendous work of all the fabulous people in the Elixir and Erlang community who have worked so hard to create the documentation to make it searchable, to format it in pretty ways, and especially the Erlang. I suspect that there's been a lot of work under the covers to sort of bring it into to standardize it similarly to the Elixir documentation, so that it's possible for Dash to be able to do this. And the Hexdoc people obviously worked extremely hard to make everything work so smoothly. I want to thank everyone who's been involved in this, because it's very cool. So there's a group within the Erlang ecosystem foundation which is focused on build and packaging working group. And these are some of the people, these are the wonderful people on this committee who I think put in a lot of time and effort to make this possible, and they deserve a lot of credit and thanks. Okay, so now let's go over to the main event for today, which is MyVal. This is the first of 7 versions of MyVal that we're going to cover. Before I start coding, let me lay out the libraries that we're going to be using as part of this. First is types and specs. These aren't really libraries, these are built into Elixir. You can see Elixir type specs. They're called type specs, they're types and specs. There's some documentation in elixir-lang.org. You can look at the Hexdocs for type specs. Here's the Hexdocs for type specs. Let me give you a brief lay of the land. So this is how you define. So a type is basically coming up with it. So here you're defining a type called word, and you're saying that it is always going to be a string. The .t here means string.type. If you're within the module itself, just T with parentheses refers to the type of the module that you're in. In this case, we don't have that. We have type word, not type T, but and then so that's a type is saying, okay, when I say word, what I mean is a string, anything that's a string, and a spec is defining a function, the function inputs and outputs, or it doesn't have to be a function, but basically the type here. So whenever I call long word, I'm expecting a word to be input as the only parameter, and of course a word type is a string type. And when I call long word, I'm going to pass in a string or a word, and I'm going to expect a Boolean back. A Boolean, of course, is a true or false. True or false are atoms in Elixir. So this is a way to specify what this function looks like, and this documentation is very helpful when you're looking at the library, because it gives you a sense of what the inputs and outputs are going to be shaped like. There are various basic types built into Elixir, like an atom, a map, a PID, process ID, port, tuple, floats, integers, positive integer, lists, non-empty lists, lists with a type. There's all kinds of, there's ranges there, range from 1 to 10. Lists, you can specify the types, or keyword lists with, so there's a lot of options. As you can tell, you can look at functions, modules, no return. You'll see this sometimes if you use dialyzer. What that means is that there's basically, it's never going to return anything. Struct, number is sort of a generic, it could be an integer or a float. You can use this pipe operator in this case to basically say it could be an integer or a float. You'll see actually the struct, the definition of a type struct includes, we talked about this earlier, that there's a key of : struct . So optional, yeah. There's also private types. So those are types that you, I think, don't want to expose. It's opaque as well. I don't use those too often, and will not explain that now. But if we ever have a use for it, I will circle back. Where's the other thing I was going to show you? Okay. I guess let's move on from that. So there's also StreamData. We're going to be working with this today. StreamData is another library that, I guess it's a library, that defines certain predefined generators. So a generator is a StreamData struct. And so this StreamData.integer is going to, it generates a stream of integers. And in this case, we're going to pass it into enum.take. And we're going to specify we want 10 values. And so this call will spit out 10 integer values. And they're somewhat random. They're basically random, but you'll see they don't vary too far from 0. But there are ways that you can make it spit out outputs that are a lot. You can shape the output distribution in various ways. You can also filter things. So let's say you start with that same StreamData.integer, and you can then say, okay, I only want positive values. I want to filter out anything that's not positive. I also want to then double everything. So you're going to have just multiples of 2. So it's going to be 2, 4, 6, 8, 10, etc. as the possible values. And then only when you get to the enum.take step does it actually generate a list of values. Prior to that, it's just a generator. Here we're saying, okay, give us 10 of these things. And generation size allows you to manipulate the output in various ways. Shrinking means that if it finds a counterexample to a test, if you use it in a test and you find a counterexample, it will try to shrink it to get a simpler version that also demonstrates the failure. So maybe a lower value or a smaller number of elements in a list or something like that. Special generators, but that's the idea, and we'll go into this. Then there's another library that we're going to use that interoperates with StreamData. It leverages StreamData but goes beyond it. It's called TypeCheck, and I only discovered this really recently, but I really like it. It does some very cool things. One thing it does is that, so it takes that type that you saw before in type specs. Type specs define type and spec, but without the bang operator here. And the difference is in standard type specs, they're not enforced by default. You can use something called dialyzer to try to detect bugs in your code through the types and the specs that you specify, but it's not perfect. If it detects an error, there definitely is an error. There's a lot of things it won't catch, and it's far from perfect. I've used it on and off in the past, and it has value, but also it's suboptimal. This feels a lot better and more powerful to me, and I'm going to demonstrate why as we build up this myval library module. But let me just briefly explain some of what it's doing. So here, one of the things that's so great about this library is it leverages the existing types and specs and just redefines them and makes them more powerful. So you can take your existing, if you already have a library and you've got types and specs in there, if you just add the bang at the end of them, it will leverage all the stuff that you've already written and then make it more powerful through this TypeCheck library. And so similarly with the spec here as well. And it's using the same definitions earlier, like integers, the same, it's not called with the parens here, but it's the same thing as the integer that we were just looking at. So it's using the built-in types as well, and the Boolean we saw earlier. So it's very similar syntax, just with adding that bang. But what it will do here is it will do checking. So if you then call something with an invalid input, it will blow up and complain. It'll say the call failed, and it will give you very specific explanations for why the call failed. So it says because parameter 1 does not adhere to the spec. So it's expecting a user struct with these keys, but instead you passed me a string foobar. So here you can see the call site. We're passing in foobar, but the spec says we need to receive a user spec. So this is pretty cool, and it fails in various ways that detects problems with your runtime function calls. And yeah, I'll show examples of this. There's also, it also defines a certain type of stream data. It builds off of the stream data library, and I think adds some ways to wrap stuff and create more sophisticated streams. And what's this? This is, yeah, it has pretty good documentation for such a, I think, young library. So I'm very excited about this. So let's start looking into that. So that's types and specs, stream data, and TypeCheck, and here's some links you can follow if you want more information. So what I'm doing here, so mix install will basically go out and grab the libraries so I can use them. So TypeCheck and stream data I need. I think this was actually a mistake because I'm doing, if I were doing this in a Phoenix library or something, I would want to say only test. But I think in here, because we don't distinguish our environments. Oh, I've already run this, so it won't let me rerun it. But I think, yeah, we don't want to specify only test here. I think I've already run this too. But create the, so now this is what I started to build out. So I wanted to have a demonstration library and demonstrate how I would build a module. And this is my first attempt, and we're going to have 7 different versions of this that get tweaked over time. But okay, define the module. Here I'm going to say, okay, I want to use TypeCheck, and I'm going to create this as a struct. So, and my struct is only going to have one key, which is history. And the idea here is that, okay, so I want to do operations and change the value with each iteration of each operation, but I want to keep the whole history. So history here is going to store the history of all the operations that or all the changes to the value. So, and so there's a type T. I mentioned earlier that T is the type for the module that you're in. So in this case, myval.t is the same thing. Within the library, you can just call it T. But if you reference it in any other library, any other module, you would refer to it as myval.t. So the type T is equal to a struct, a myval struct, with a key of history. And that value of that key has to be a list of numbers. So list can specify what type of list it is. By default, Elixir lists can have mixed values, mixed types inside. But here I'm specifying that history has to be a list of just numbers. So the first 2 function clauses here are val. And I'm saying, okay, if somebody calls val and passes in a myval, and there's no history, then we just return nil. If somebody passes a myval into val and there is something other than an empty list, we want to take the head, we're pattern matching the head here and just returning the head. So we're just getting the most recent value. So we're going to build up the history of all the values as a list, and when we add a value to a list, we add it at the head. That is the efficient way to do it. If you add it to the tail, it's very inefficient, especially as the list size grows. So we always add at the head. So the leftmost, the head will always be the most recent addition to the history. So now we're going to define 4 functions. You might guess what they're doing. The first one here is add. So what we're doing is we're adding a new val. So we get new val here. And we're taking the existing myval and we're adding new val to it. And we're saying, and this is a guard clause, we're saying when hist, basically the value of the history key is a list, because it should always be a list. So in this case, we're gonna take myval, which is the structure that we passed in, the myval that we passed in as the first parameter. And then we're going to pipe it into the val function, which we just defined up above. The val function takes a myval and returns the head of the list. So if there is a value in there, val will be set to the initial value that's in the history. And then what we're going to do is we're going to take the myval that we passed in. Again, this is the myval. What this section is saying in add, by the way, is saying, okay, so the first parameter that gets passed in, we're going to assign it to myval, and we're going to assert that it is a myval struct with a history key whose value is a list. That's what this is all saying. But now we have myval stored as myval, which we're putting here, and then we're saying, okay, so we want to return a new val that's based off of myval, but where the history key is equal to this. And what this is we're taking the hist, which is the initial history, so that's a list of numbers, and we're appending, that's what this pipe operator here is doing. When you're inside a list and you have a pipe operator, you're saying, okay, this should be a sublist of the full list that we're defining. So this is the existing list, and we're going to prepend, we're going to prepend a new value, which is val plus new val. So we're taking new val, again, is the number that we're adding, and val is the head of the existing history. So we're taking the most recent value, which is the head of the list, hist, and we're adding the new val, which is the val that we want to add in. And we're going to add that to the history, which is a list of numbers. Very similarly, subtract does the same thing, except it gets the head of the existing history. But here, the value that we prepend to the history list is val minus new val. So we're subtracting the new val. Similarly, multiply, we're taking the new val and we're multiplying by the most recent value in the history. And for divide, we're taking the new val and we're dividing by the new val. So the most recent value in the history divided by the new val. And so this is giving us 4 operations that we can play with. Each one will take in 2 things. It'll take in a current myval and a new val, and we'll apply an operation and return a new myval with an extra value prepended into its history, which represents the result of that operation. And then I define one last function, so I want to be able to view the history. So I said view, okay, if you pass me a myval, I will show you the history and or I will show you information about it. So here I'm defining a map, and there are 2 keys. One is val, which is just saying call myval.val on myval. I don't have to actually spell out myval. I think I could just say that. That should work too, because it's a local function. I should probably do that, or if I'm going to do anything, I should do this in case I ever want to change the function, but this is actually the right way to do it. And then, so we're going to get the most recent value, which is the current value, and we're going to get myval, which is the whole data structure. So it'll print out, it'll return the whole structure. Next thing I did or tried to do didn't work, and I'm not sure why, because I did. So here I'm doing a def impl. So I'm trying to override the inspect protocol for my new myval. What I wanted to do is I wanted to define inspect so that it would automatically print out just the most recent value in the history. So I was taking the myval struct and just pulling off the most recent value in the history. And I wanted to just display that, and that would have been pretty cool but it didn't work, and I'm not sure. It says the inspect protocol has already been consolidated, so doing this has no effect. This worked. I did this in episode 101 with the player struct, and it worked. And I'm not sure why. I'm doing basically the same thing here, and I'm not sure why it's not working here, but my suspicion is that it's because here we're using TypeCheck, and I suspect that it's maybe playing with, it's consolidating the inspect. I've seen in the documentation that the consolidation happens once, I think at compile time for efficiency reasons, but I'm not really sure what's going on here. But my attempt to do this, which it would have been cool, didn't work. So just wanted to mention that it didn't work. Maybe somebody can suggest something that might work there, but I'm going to move on now. So let's use this. So here I'm creating a myval struct with a history. So this would have started out as -8. Then maybe I added 12 to, added 11 to it and got the value of 3. Then I added 4 to it and got the value of 7. Now I'm going to add 8 to it. I'm going to get the value of 15, hopefully. And instead of just returning the myval, I'm going to do this myval.view. And it was already there, I think. Yeah. So again, the value, the latest value is 15, but I'm also printing out the full struct. In which case we see that it started at -8, then became 3, then became 7, then became 15. Here we do a bunch of operations and you can see the full history, and it ends up with a value of 9.0. The reason it switched over from integers to floats is because as soon as you call, I think divide always makes it returns a float. Multiply might, but I think it's divide here that's turning this into a float. Actually, we can find that out for sure. I'm pretty sure it's divide that's turning it into a float. Let's skip that step and see what happens. Yeah, so now we're getting an integer again. So whenever you call divide with the slash, because that's what's going on under the covers, it becomes a float. If you want to do integer division, you want to use the div command rather than the slash. The slash is the slash is always going to do give you a float. So this is the first cut at creating this library. Let's move on to the second version. So I need to move in here, and we're going to open up this live book. Again, yeah, I think we want to keep this. That's not what I wanted to do. Let's see. Try again. This piece of it. Let's see if that works now. So what did I change? So I added functions. These are notes to myself to remember what I did at each step. So I added some new functions. So the first thing I did here, there's a new function here, new, which is taking a value. And so this is now instantiating a new object, because earlier I couldn't handle the case where there was just a nil value in there, and so now I'm creating a function myval.new, which will instantiate a new myval. And I also realized that let's first talk about how did I change the what did I change here? So there's this data structure here. Let's look at this for a second. So this is for subtraction. And so this is an operator. This is the subtraction operator. And this is the new value. New value here is actually the old value. I think I redefined this for clarity in the next, in the third iteration of this function. But this is the new value that you're going to subtract. So this is basically saying, okay, this is a data structure representing the operation that we're applying. So here we're saying, okay, we want to take our myval and we want to subtract this new value. And so this here is saying what the operation is that we're doing. So we're subtracting new val. So if new value is 3, then this will be the minus atom and 3. Or up here, it's similarly, let's go multiply. So the operation is a multiplication, and so we multiply by 7 or whatever. So here we're going to record all the operations. So instead of only recording the values at each step, I also want to record the operations that were applied to get that value. So this is where it got messy, because every step in the process has both an operation and a value, except for the very first step. The very first step, there is no operation to get there because you just start with a value, and that's why this has to be nil. And this got kind of ugly. It's a messy problem to handle, but I started here and then I evolved it. So let's go with this is my first cut at this problem. So what I did is, so I'm saying, okay, we started with nothing, so there was no operation to get here. We just started with a value. So so let's say we said the value, we called myval.new with the value 10. Then the new data structure would be a myval with a history with one element inside it, and that element would be a tuple with 10 as the first element and nil nil, a tuple of nil nil as the second element. We'll see down below. Actually, maybe I'll just show the first example before I continue on. So that we skip. Okay, so let's see what this does. You'll see here. Okay, so then I'll go back to the code, but here's the idea. So as before, whenever you view the myval, it will give you the val back with the most recent value, which is 15. That's the last calculation. But here, instead of just seeing the history of the values, -8, 3, 7, 15, here you have the operations that were performed at each step. So you could distinguish like multiplying by 2 versus adding 2. Even if they gave you the same value, they might be different operations. So here we're saying we started with a value of -8, which had no prior, that was not created by some other operation. It started out as the value -8. Then we added 11 to -8 and we got the value of 3. Then we added 4 to the value 3 and we got 7. And then we added 8 to the value of 7 and got 15. So now we have a richer history of how this value evolved. Now that you hopefully see better what we're doing here at this step, let's go back to the new code. So this is a way to create a new instance of myval with no history, just a single value. Let's see so, and here I've had to redefine val. We don't care about the operation, the last operation. So this here is the last operation and the last val, and we don't care about the last operation or the last operand that got us to the last val. We just want to know what the last value is, so we get the head value and return it here. I created a new function called peek, which is taking the history, and what it's doing, so it's returning the full myval data structure unmodified, but it has a side effect. We're doing an IO inspect, so we're going to print out the value of head val, which is the most recent value, and we're labeling it current value of myval instance. So you could stick this into a pipeline, for example, if you didn't want to change the value flowing through the pipeline, you wanted to pass myval through each time, but you wanted to peek at what its value was, you could stick this in your pipeline, and it would, as a side effect, output the current value of myval with this label, but it would then pass the full myval data struct through to the next step in the operation. Here again, we have the same 4 functions for the operations, but we've modified them so that we're at every step we're recording the operation that was performed as well as the new value. So this is the full new thing that we're adding at each step to the history. View again, yeah, that probably hasn't changed. I created a history which takes the history, it pulls the history out of the myval struct and then reverses it. And the reason is because we're building up the history from right to left, but we want to display the history from left to right. So that's why the reverse is there. I call it show history. This is a little trickier. Let me first show what show history is doing, and then we'll come back to the implementation. By the way, yeah, so I didn't execute these, but they all work. So this is showing the history, and you'll see it's nicely formatted so that you can see the full history. But again, this is going from right to left rather than left to right, because this is just displaying the history. It's going bottom to top in this case, which is, if you printed it out as a single horizontal thing, would be right to left, and what we want to do is print it the other way around. So here's show history. Show history will print it in a prettier way. So what we're doing, we're starting with this value of -8. So I'm printing it out as a list of strings, and the first string is just -8. The second step, we added 11 to it. So here, the second step in the shown history is +11 equals 3. The third is +4 equals 7. The next one is -8 equals -1, etc. And then you can see here where it transitions from, you get 100 minus 10 is 90, and then we do a division by 10, and that's when the value goes from being an integer to being a float. So this is just a pretty history, and so let's go look at the implementation there of this history. I did 2 implementations. So we take the myval, and the first thing we do is I call something that I call another a private function call that I created called first rest. So I pass myval into first rest. So let's look at what first rest does. So first rest is here. What it does is it takes myval, it then calls history, and then it calls list pop at 0. And what that's doing is it's splitting the list into 2 pieces. And returning them as a tuple. So the first piece of the list is going to go here, and the rest of the list is going to go here. So the first element, the 0th element of the list, is going to be returned as the first element of the tuple, and then the rest of the list is going to get returned here as a second element of the tuple. So I'm calling it rest, but the first value is going to be that. And so we're splitting this into a tuple. I didn't since I'm not using these values, I could just comment this out. It doesn't actually help to have that line there. What I'm really doing is when I call this, it's going to return a data structure like that. So a 2-element tuple, with the first element being the 1 element and everything else being in rest. So where's first rest? So we're calling first rest, and now we're pattern matching against the result. And so again, this first case where it's nil keeps messing me up, because I'd like to have a nice clean thing where every step is identical to every other step, but because that first step doesn't have an operation, it keeps getting messy. So now I'm going to do a reduce over the rest of the list. So these are all the operations that don't have nil. So, and I'm going to, so we're going to build up, this is the accumulator. In a reduce, you start with an initial value of your accumulator. The initial value of the accumulator here is going to be a string with the value of first. So it's what we pulled out here. So like if the first value is -8, it's going to say -8 here, but it'll be as a string. And then we're going to reduce the rest of the list, and every other step in the list is going to have an operation and a value. And so enum reduce is going to start with this array as its starting value, and then it's going to loop through all the rest of the stuff. And at each step, it will call stringify next line. So let's go look at the stringify next line. So you see stringify next line has 2 function clauses. The first function clause is for the case where the operator and operand are nil, in which case it will just actually looks like it's doing the same thing here. I'm not sure why I'm stringify entry. Actually, these do exactly the same thing, so I think I can get rid of, I can just call this once. But so stringify entry, when it's nil is going to pattern match here, and it's just going to print the value. So for the initial, and so actually I might have been able to get away with starting off with the first value included as well. But and then if there is if it's anything other than nil, we're going to assign the operator to op, and we're going to assign the operand to operand, and then the return stringified entry is going to say, +7 equals 13 or whatever it might be. So we're starting off with like -8, and then we're looping through all the operations and values, and at each line we're adding one more string to the result. And then when we get to the end, we want to reverse it, because we want this to display from left to right, but our history is we're adding elements to the list in the opposite direction. So that's how we did it. This is a second way to do the same thing. I'm not gonna, since I'm already This is going to take a long time to finish this presentation. I'm going to skip it for now. We have recalculate. I'm going to use recalculate later to show off property-based testing. But what recalculate is doing is it's recalculating the most recent value by taking the initial starting value and then applying every operation in sequence to it. And so, because inside our history, where's our history? I want to show an example history. So inside this history, we build up. We save all the values at each step, but we also save all the operations. And so the point is that this value here, which was pre-calculated and stored inside history, should be equal to taking the starting value and applying this operation to it, and then applying this operation to the result, and then applying this operation to the result, then applying this operation to the result, etc., until we get to this operation, at which point we should get to 9.0 again. So that's what recalculate does, is it goes through the history. Yeah, so we're reducing through the history of all the operators and operands, starting with the first value, which we're pulling out. So we're doing first rest. So the first element we pull out is pulling out the original value that we started with, and it's starting there, and then it's applying all the operations in sequence, and it's applying it through this apply method, which is a kernel method. With apply, you pass it three things. You pass it a module, and then a function, and then a list of arguments. So this would be the same thing as calling kernel dot whatever the op is. So in this case, it would be, I think it would be like plus, and then the two values. Oops, where did it go? I can't see the screen because okay, ACK and operand. So I think this is equivalent. So what we're doing here, but we're applying it, so this can be dynamic, because we don't know what op is. It could be plus, it could be minus, it could be division, it could be multiplication. Because this is dynamic and these values are dynamic, we use apply to apply a module function arguments list. And so at each step we're applying this, and so we're building up each step of the process, the value based on all the original value and all the preceding operations. And this should be, the recalculate value should be equal to the current most recent value. And we'll have some property-based tests of that to verify that our functions work correctly. So that's the basic idea of how we built this up. Here's examples. You can get the idea. So the show history 2. So it's two different ways to generate the history, and they generate identical results. And here, so here's the peak thing. So if I do this peak, it continues to pass the value through the chain, but I can see that, well, at this point in the process, the value was 1 million, just over 1 million. Then I divided by 100, and so we ended up with 10,000, a little over 10,000. But I peaked at the value at that point without changing the value that flowed through the pipeline. Okay, so that was version 2. Let's go to version 3. So again, we want to get rid of this only test. I'll remove this before I'll save another version to the repo afterwards. So here I'm adding types and type specs. So, and you'll notice that there's a lot of things commented out here. I struggled with this because the fundamental problem was that the lists have different types in them. There's two different types. There's the types that have operators and operands, and there's the initial value which does not have an operator or an operand. They're nil. And I tried a bunch of different ways to be very explicit about the fact that the list should have an initial value which has a number and then a tuple with nil nil, and then all the other values in the list should be number with an operator and another number. And I struggled with that and eventually gave up. And then I think the next version of this that we're going to see, I went with a different approach altogether for implementing it. But let's look at what this step came up with. So I defined a new type called myValOps, which needs to either be a plus, addition, subtraction, multiplication, division, or nil. MyValEntry is going to be a tuple with a first value of number and a second value of a myValOps, which is one of these things, and then a number. Or it's going to be a number and a myValOps and nil. And I played around with different ways. I tried to do nil nil, and a lot of things didn't work for me. It was frustrating. But it's because it's this weird edge case where I have a list. If it were a tuple with different types in it, it's easy to specify that. But when it's a list, and if the list has all the same types in it, that's easy to specify. If the list can have any kind of types at all in it in whatever order, that's easy to specify. But where you have a list where the first value in the list should be one type, and all the other elements in the list should be some other type, it's confusing, and I don't know how to do that. And then so the type T that we had before, I've slightly redefined it. So the myval has a history with a value that should be a non-empty list of myval entries. So these things. Then I have then I created specs. So when so new is expecting a number, and it's returning a myval data type. Val is taking a T, which is in this case a myval.t, so a myval data structure, and it's returning either nil in that first case where you don't have a value of any kind, or a number. Peak is taking in a myval type and returning a myval type because it just passes along the value. It has the side effect of printing out a value to the screen, but it's just a side effect. It's returning the myval data structure. Add, actually all add, subtract, multiply, and divide are all taking in a myval type and a number and returning a myval type. View is taking in a myval type and returning a map with two keys. One is val and one is myval. Val needs to be a number, and myval needs to be a myval type. Ordered history is taking in a myval type and returning an ordered entry list, which we defined up ordered entry list. That's non-empty list of myval entries. Show history is taking in a myval type and returning a list of strings, as is show history 2. That should say show history 2. Oh yeah, I think that was a typo that I caught in a later version. Recalculate is taking in a myval type and returning a number. And then these are private functions, so I didn't bother creating types for them. Not sure if there's anything worth explaining here. Oh, I didn't want to hit that button. I don't know what I just did. I wanted to I just reloaded the page, so now I've lost everything. Let me, okay, I think there's another way to do this. I'll just run everything. Okay. When it evaluate, you can see it like queued, and then it'll start counting how long it's taking, and then when it's done, it will say evaluated. So now I've just run everything, so now we can see everything. Okay, so yeah, so now we start seeing some of the benefits of TypeCheck. So here, when we try to pass in an invalid input into myval.new, TypeCheck won't let us do that. It says type error. Unfortunately, the live book formatting doesn't seem to work too well with this. I think they're using a font color of white, which doesn't work on a white background, but the information is on. Let's see if I can highlight everything and see it all. The call to new failed because parameter 1 does not adhere to the spec number. So it's expecting a number, but it got the string A. So it's telling us exactly what the problem is. Here also we're getting it's blowing up but there's a lot more detail here because let's see what is going on. Parameter 1 is it's expecting a myval.t, but instead it's just myval history with this thing here, which takes a little explaining here. So this is because lists and, well, actually I'm not going to explain this now. It is a list of integers. If those integers are mappable to, I think, ASCII characters, they will sometimes get displayed as a list of ASCII characters rather than as a list of numbers, because Elixir or Erlang thinks it's being helpful, because if you want to, in the original version of Erlang, if you wanted to store the string, let's say cat, the only way to do it was as a character list, which was saved as a list of integers. So the list of integers was identical to the string, the character list CAT. So I think that's what's going on here. You can ignore it, but the point is that we're passing in a list of numbers here, and that's no longer valid. The original version of this myval struct, that's how I did it, but that's no longer valid. History doesn't look like that. It needs to be a list of tuples. Again, yeah, the spec myval.t. Yeah, it needs to be a myval.t, and it's not. And there's a lot of details there that you can ignore. But if you create this, if you create a myval manually and it does match the data structure, it will work. But if you do an illegal operation, it will stop working again. So here I'm trying to add 3 as a string rather than an integer, and it blows up. It tells me I can't do that. Subtracting 3, etc. Peak still works. Now we're going to show some example-based tests. So there's two main classes of tests. Traditionally, people focus on example-based tests, where you spell out the inputs and the outputs that you expect, the inputs you want to pass in and the outputs you want to expect to get out of it. We'll start there, and this is really good for if you have, for example, edge cases that you definitely want to test. You want to create example-based tests for those specific edge cases. But we'll also cover property-based tests in a little bit, which is a different way to do it, and that approach allows you to explore a lot more possibilities, some of which you might not have thought about. But let's start with example-based tests. Here I'm using XUnit, which is sort of the standard test framework built into Elixir, and I'm going to require myval, which is the module under test. That's what I want to test here. I'm going to define a setup block. So these are the tests down here. And if I define a setup block, what that will let me do is, actually, yeah. So in the setup block, I can define things and then share them with all my tests. So in this case, the setup block, I'm defining steps. So I'm defining a list of functions I might want to call, and then I'm returning them. So I'm putting steps in here. So each test block will have access to starting value 99 and steps, this list here. This first test isn't going to use the setup. It's just going to define its own test. This is just how a test works. You call assert, and then whatever comes after assert needs to evaluate to true. In this case, 3 does equal, again, double equals is equality operator. It's not a match operator, it's equality. So 3 is equal to 3. So that passes. Here, we're going to, in this test, we're going to grab the starting value from the setup block and assign it to the local variable SV, and we're going to assign the steps, grab the steps from the setup block and assign them to the local value of steps. We're going to take steps and we're going to throw it into an enum reduce. We're going to start the initial value that we're going to reduce, the initial accumulator value we're going to reduce with is a new myval struct with a starting value of SV, which is 99 in this case. And then we're going to reduce over all the steps, so these are the steps, with this anonymous function, what the anonymous function is doing is it's taking the accumulator, which is initially a value of 99, and it's going to take this tuple of operator and operand, which is add and 1, divide and 10, multiply and 2, and subtract and 10, and it's going to apply module function arguments. So the first step, it's going to do myval op, which would be add. It's going to add 1 it's going to call the add function on myval with these operators, the accumulator, so that's the initial value of 99, and the operand of 1. And it's going to go through all of those, and then it's going to assert. This is a. I'm saying, okay, we're going to do this operation two different ways. We're going to generate final my value, and then we're going to grab the value out of there because final my value. We're started with a myval data structure, so we're going to end up with a myval data structure, but it will have a history, and we're going to then grab the last value out of that. We're also going to take final my value, which again is a myval with a history, and we're going to call the recalculate function on it, which is going to reapply all the operations in the history against the initial value. And what I'm saying is that these two values need to be the same, and you'll see that they are. They passed. The test passed. So that was my first effort at testing this library or this module. Let's now go on to version 4. So TypeCheck didn't like name types inside other name types. I tried a whole bunch of things, so I modified this again. I guess I'm not going to go into what I did here, but yeah, I had to change this because the types didn't work out very well. Let's see, what do I want to cover here? This is all pretty similar to before, I think. So spec test. This is one of the other benefits you get. So here I'm doing TypeCheck XUnit. And so, well, first of all, please notice that this async true is a benefit you get from XUnit and Elixir. If you're able to avoid sharing state across tests or needing to hit databases, there are times you don't want to call async true, but if you can, this will allow you to speed up your tests by running them asynchronously in parallel. So what we're going to do, let me just, I'm going to run everything so I don't have to hit enter for every cell. You see queued, it's taking 3 seconds. That step here took like 3 seconds. Now this is evaluated. So it did succeed in generating this, and it did not throw an error, so I think that means it passed. Yeah, that thing didn't work again. I know that. That didn't work. Yeah. And my val history. This is all looking the same. Where we showed this before. More tests. Okay, so this is now I added some more tests. This is an invalid data structure, and it's telling us so. This is an invalid data structure. It's telling us so. Same thing here. This is an invalid passing the quote. This works. Okay, then that's the one. Oops, spec test failed after 17 successful runs. Oh, good. This is good. So I think, I'm not sure if this is the one that I hit. Yeah, divide. Yeah, so it's doing. So what it's doing is it's running the spec test over and over again, and event. Oh, I think this test failure is actually for. I think it's at every step it's running all the tests, including the ones down below, and then spitting out the output in one place. And I think it's because I'm doing XUnit run. I'm not limiting it to just this cell, which is unfortunate. but I think these failures are based on type checks that are actually happening down here. I'm probably not sure what's going on. But when I was doing this earlier, when I was creating this live, I hit a case where basically I was dividing by 0. And I hadn't thought about that. But oh yeah, and that's what's going on here. You can see spec test failed after 17 successful runs. So it tested 18 times, and 17 of them passed, and then it hit this case and failed because it's generating random inputs to the tests. And the idea of property-based testing is eventually, if there is a problem, eventually it will catch it. It may take a long time depending on how subtle the bug is and how likely you are to hit that set of inputs that triggers the bug. But in this case, this is what happened to me at this stage earlier when I ran this earlier, is I eventually ran into this divide by 0 problem. So it initialized the value with this minus 0.019 case, which I hadn't even thought about. I said number, so it's generating, decimal floats, which is great. That's not the problem here. The problem is it then tried to divide that by 0, and obviously that doesn't work. And so when I saw this, I said, oops, yep, got to rework my library to take into account the fact that we can't divide by 0. So let's move on to the next, so version 5. Let me evaluate everything. Okay. So again, this is actually getting cleaner. So, oh yeah, I think I redefined some things here. So I spelled out that an action is a tuple with 2 things in it. And this is actually a lot clearer, and I wish I had thought it had this level of clarity when I first did this. But so my valops, so the action is one of these things, a tuple with a first element, one of these things, and a second element of a number. And the actions type is just a list of actions. And then a change, so here I'm distinguishing, so what an action is an operator and an operand. And a change is the combination of the previous value and the action gives you another number. So a change is the new number and the action that generated the new number. So this is just defining cleanly what we were seeing in the earlier versions of this program. And so changes is a list of change types. We still have ordered. Oh, and so now you can see it's nice and clean. The myval, I've redefined it. It's no longer a history with a list of things in it. It's now, I've broken up into 2 different pieces. So I finally clarified. I hated the fact that I had a list with 2 different types of things in it. I had the first value, which is a value, and then a tuple of nil as the operator and operand. And then I had all the other values that were a combination of the value and the operator and operand. And I didn't like the fact that those were two different types of things. So I refactored the code so it works the same, but under the covers works differently. And that's one of the reasons you want to keep your data structures sort of hidden and expose them through functions. So you have the freedom to refactor as you see a need to do so. So in this case, I refactored, and instead of starting off with the history list with an initial value that doesn't include an operator and operand, I explicitly spell out a starting value, which is just an integer. Start val is just a number now. Sorry, it's not an integer, it's a number. And then a list of changes. And changes is a list of change tuples. A change tuple is a number and an action. An action is a tuple with a operator and a number. So this is much cleaner. This feels nicer. It's just now I have 2 things instead of 1 in my data structure, but it feels cleaner and easier to operate with. So I redefined everything. So initially, changes starts out as an empty list, of course. So when you create a new myval, you assign the val to start val, and changes is nil. I now created this thing called apply action. So you'll see, where is it? So we still have add, subtract, multiply, and divide here. These functions still exist, but now we have something called applied actions. And what does applied actions do? So it takes the myval data structure and a list of actions, and it returns a new myval. So basically, apply actions is going to take this list of actions and loop through them, and that's what's going on. After actions, now we're reducing. We're starting with where's MV? So this is the myval. What am I doing? Yeah, so we're going to apply. We're going to apply the actions to the myval step by step. Where's this here? So the actions are. So this is pattern matching. So apply action. So all four of these functions have the same first parameter, which is just the myval data struct. But the apply action, there's four different actions that can be taken. So if the action that you're applying is plus, then we're going to call add. If the action you're taking is minus, we're going to call subtract. If the action you're taking is multiply, we're going to call multiply. And if it's division, we're going to call divide. And we have those functions here. And let's see, so we still have peak. We've redefined peak slightly, but it's basically the same idea. Val is simpler now because we have the starting val. We're just going to look at starting val. That's all we need to look at. Oh, sorry. No, that's if changes is empty. If changes is an empty list, then we just get starting val because that's the only value we have. In any other case, when we call val, we're going to get the head of we're going to get the most recent value in the changes list, which is the head of the list. Again, a lot of these things have changed slightly because we've changed the data structures, but you can look at the details. It's similar logic. It's just the details have changed. So now we do the spec tests, and yeah, this didn't work again. I kept it in there, but it doesn't work. But the functions all work as they did before, so none of the behavior has changed here. It's just the implementation has changed. And but I didn't. Did I cover the division by zero thing at this step? Let's see, divide. I did not. So I think actually I misspoke. So it's at this step I think where I found the division by zero problem. So right here there's no logic to cover the division by zero problem. The next step will presumably is where I fix that problem. But so we may see that problem recur here. Let's see if we do. Type check errors. So here we're running these tests. These all passed. Oh no, failure. We got a failure. What was the failure? So a lot of the tests passed, but eventually we hit a failure. So here we go. Yep. Recalculate, divide by zero. So it tried to apply the function to divide by zero, bad argument, and an arithmetic expression. So so here I'm actually building out the StreamData. So I'm importing StreamData from the TypeCheck library. So this isn't the standard StreamData. This is the specialized StreamData from TypeCheck, and we're using TypeCheck. We're creating a generator where we're building a list of we're building myval actions out, and then creating a generator from them. And we're returning, this is in a setup block, so we're going to pass this to all the tests. So this test is going to grab that, and so myvalgen is the generator. And then we're saying, okay, I want a list of I want to use this generator to generate a list with 50 elements in it. And then I'm going to take one set of 50 and then print out that as sample data. So here is sample data. There are presumably 50 things in there. It stopped counting them at some point, but it's a whole bunch of operations. That's just showing how this didn't actually run anything in the test. That's just showing how to generate the data. It's showing that apply action works. Then here you'll see failures as well. So bad argument in arithmetic expression. Here we're actually running the test, and this is where it's actually failing. So let's look at the details of what I did here. So we're building the action generator, passing it into the test here. We're defining max action length. So we're saying we don't want super long actions. 20 actions is enough. And we want to do 10 tests. We can change these things to generate more or less random stuff. We're saying starting values. So here I'm explicitly saying, okay, I want a starting value somewhere between -500 and positive 10,000. And we're going to take num tests. So we're going to generate 10 tests. So we're going to take 10 starting values and assign them to start vals. And here we're going to take the actions generator, which is up here, this TypeCheck, building the actions out. And notice it's building the actions not from a pre-configured thing, but from my definition in my val of what an action is, which is a tuple with a first element of plus, minus, divide, or multiply, and a second value of a number. So it's generating a random stream of actions, where an action is what I defined it to be. And then it's generating these actions. I'm saying, okay, give me a list with a maximum length of 20. Give me 10 sets of those lists, because I want to do 10 tests. So I'm going to have 10 starting values, and I'm going to have 10 lists of actions. Oops. I can't get it out. And we're going to inspect it. Let's see what it looks like. It should be down below. Oop, it blew up here. Here. So these are my 10 starting values. These are my 10 actions. So that there's 10 lists here. So this list just has one thing in it. This has 0 things in it. This also has 0 things in it. This here has 4 actions in it. This also has 4 actions in it. So we said up to 10 actions. This one here, 1, 2, 3, 4, 5, 6, 7, like 7 actions. There's a lot here. So all these things are going to work, but you'll see, where's the divide by 0? Somewhere in here, there's probably, oh, here, this one's going to fail, because this is going to try to divide the current value by 0, and that's going to blow up. And that's exactly what happened. So that's where we got the error message here. We're trying to divide by, where's it saying? Arithmetic, bad argument, divide. Well, we've seen it before. So now we know we need to handle the divide by 0 problem. And I presume at the next one, we will get to that. So that was step 5. So we want to go to step 6. Let's evaluate everything. Oh, so let's see if I fix the, yeah, it looks like I fixed it here. So there's division, apply actions. Oh, so I did something else here. So I said, okay, any invalid action, if there is an invalid action, so we're going to, before we apply a list of actions, so apply actions is taking a list of actions here. And before I try to run through the actions, apply the actions, I'm going to check them and say, are any of the actions invalid? And here's the definition of any invalid action. So it takes a list of actions and it looks to see, is any of the actions of this type where the operator is division and the operand is 0. And if any of the actions in the list has an operator of division and an operand of 0, then it's going to be true. And if it's true, we're going to take the myval data structure, and instead of doing reduce and applying each action in one by one, we're instead going to invalidate and wrap in divide by zero error tuple. So invalidate and wrap in divide by zero error tuple. So I'm taking the myval, invalidate due to attempt to divide by zero. So we're invalidate due to attempt to divide by zero. So what this is going to do is it's going to grab any errors that are already exist. Now the myval type has a new key called errors. We're going to grab the value of errors and we're going to add this error to the list, which could be an empty list. Attempted to apply an invalid action to this myval instance. And then we're going to modify we're going to return a new myval, which is based on the old myval, but we're going to have again, there's a new key in myval here called valid, and we're going to say it's false. And we're going to put the new errors list in, which will include this error message. So that's the invalidate and wrap and divide by zero error tuple. Oh wait, that was here. So which called out to this. And then the next step, what it did was, let's say function. Oh, so now it's wrapping in an error tuple. So it's taking the my value, and instead of just returning my value, it's going to return a tuple with a first element of error, an atom, and a second value of my value, which will have a errors key and includes this. So it will explain, the data structure itself will explain why it's invalid. Of course, if none of the actions is invalid, then we apply them all. If you pass in an already invalid error tuple and you try to do something to it, this is going to get called. So in this case, for apply actions, you'll see that it's a multi-clause function now. This is all apply actions. And the first thing that apply actions does is check whether the myval that you're passing in is valid or not. And if it's not, if the valid flag key is false, then it's not even going to try to apply the actions. It's going to ignore the actions, and it's going to wrap in an already invalid error tuple, which is here. So we're going to take the existing errors in the myval, and we're going to add attempted to apply actions to an invalid myval instance to it, and that will become the new errors key, the new errors value in the returned myval. So I'm adding error handling, and let's see, the divide. So divide. Oh, so I added error handling, but I still have not fixed the divide by zero problem here. Oh, here I did. Oh, yes, I did. Sorry, here it is. This is exactly it. So before it was a single thing where we just divided by zero. Now there's two function clauses. So if we've already filtered out, actually I could get rid of this valid true here because we've already tested in the apply action. We've already tested and we'll have caught any myvals which have valid false at this step. They'll never get past this step. So we know that anything that gets past this step already is valid true. So we can get rid of that. We don't need that here, but actually let's just leave it. There's nothing wrong with it. Let me just leave it in for now. I don't want to confuse things. But if you're trying to apply an action of divide by zero, that's going to be attempted before the more generic apply action divide by operand. So if you try to divide by zero, you won't get to this step unless you already have the myval you have is valid. But if you get here with a valid myval, it will invalidate and wrap and divide by zero error tuple. So it's not going to actually run it. It's going to put an error into the data structure, and it's going to return a tuple with error and the modified myval to the user. Of course, if you have any other type of division, it will happen as before. So this should have fixed the problem that we had before of division by zero. And so now everything hopefully is passing, aside from these things. And you'll see now that the data structures that we're returning are more complicated. There's a valid true item here. There's also an empty list of errors. Same here, valid true. These show history functions still work as they did before. The peak still works as before. This and price. Okay, yeah, these are invalid things. I've already shown them. Actually, no, this changes. Oh, I think I just modified these to. I don't think I need to rerun these. Argument. Yeah, the argument errors still happen. If you try to pass in something invalid, it's not going to work. So here, there's no starting value, and there has to be a starting value. It's telling you. So it knows what a myval looks like, and if you give it something that's not actually a myval, it's going to blow up. Recalculate still works. The tests. Let's see if they now they're passing. 14 spec tests, 2 regular tests, and everything passed. I'll come back and look at the test, but let's see if they passed. Yep. 1 test, no failures, no skips. This is apply action seems to be working. It shows you the starting value. It shows the history of changes. It's valid. Example-based tests for division by 0. Oh yeah, so now because we caught this problem with division by 0, once your generators, your property-based tests discover a problem, you want to make sure you add an example-based test for each of those cases, so you never skip it anymore and you always handle it properly. So what are we doing here? We're going to create an example-based test for that. We're going to make sure we prevent division by 0 in our property-based tests, and we're going to generate actions and build a valid myvals by apply actions. So still building up a list of actions, but here so here we have an example-based test where we simply tried to divide by 0. So we take, at this step, it's a valid myval, and then we try to apply an invalid operation to it. And we're going to assert that the result sets the valid key to false and returns an error tuple, which it does. Again, same thing here. This is just redundant example. Actually, it looks like so here I'm doing explicitly dividing by 0, or trying to. Here I'm saying apply action, so I'm trying to do the same thing but with a different function call. So and both of these are failing exactly as desired. Attempting to apply actions. So this is apply action single. So here I'm just applying a single action. Here I'm applying a list of actions, one of which is division by 0, and this is the case where we wanted we don't even want the actions to run. So actually, I could be inspecting what the error. I should probably be doing that is confirming that the correct error. There's an errors key in here. I should be checking that there's a value in there that is the correct error message, but I didn't do that. Remove divide by 0 actions. Oh, right. So now that I've explicitly hard-coded tests for the division by 0 case, I need to modify my property-based tests so that I don't keep hitting that because I've already explicitly tested for it. So I'm going to avoid that problem in my property-based tests by always removing any actions that are calling for division by 0, because I've already covered that case and I don't want to overcomplicate this stuff. So what this is doing is, okay, you pass in a list of actions, and I'm going to call enum reject. So anytime that you get an action where the operator is divide by and the operand is 0, we're going to reject it. So this is just going to return a list of actions, but having filtered out enum filter filters in values, enum reject filters out values. So anytime you see that, just kick it out of the list. So now again, we set up our test with the starting values and the actions each step but we've added this step here, enum map remove divide by 0 actions. So we know that it'll generate a list and then it will remove any that are divided by 0. It would actually be better, instead of doing it here, I should have added, what I should do is I should go to here and create a different generator. So here I'm creating the generator. I should have the removing the divide by 0 steps removed from the generator itself, and then it would be useful everywhere. I did it here, it works this way, but it would be better to do it up above. It just occurred to me. Here I'm using enum.zip. This is, yeah, I guess I'm not going to go into all the details here, and I'm looping through all the tests, and at each step, yeah, this is getting complicated. I can't remember what I all did here, but actions applied. So I'm taking the, what are we doing? Okay, actually, let's look. Actions applied should be down below. My vals, actions. So this is the list. Each of these lists here is going to be used in one of the tests. So the first test will be like using the starting value of 90, 90, and this empty list of actions. The second test will use the starting value of 98, 72, and this list of actions, etc. And there should no longer be a divide by 0 action anywhere in here. That's the list of things. My vals. Oh, right. So now after we've applied the starting values and the list of changes. Okay, yeah. So each of these. So the first list, there's no changes. So these are the starting my vals, which I've created by taking the start val and the list of changes. So here, this is the starting val, and these are the list of changes. Oh, I know what I did. Yeah, so this was complicated because the generator of the actions needed to match up with the... you couldn't just generate random actions. The actions, because they include the value of applying the operation to the resulting value of the previous step, they needed to be correct. So that's why I needed to generate those myself. And that's what all this is doing here. It's extra complicated, but it does work, and you can look at the details yourselves, but I'm not going to bore you, and the tests do pass. Let's see what I forget the last version of this did. 6, so we're close. We're just one more version, then we'll be done. 7. Where's 7? Oh, let's run everything. Just that. Actions. Did I change anything? I can't even remember what I did. It's been like 3 weeks since I built this originally, so I'm struggling to remember all the details myself. But the tests are passing. What did I change? There should be a note somewhere saying what I changed. Oh, it's cleaner tests here. I think I named this function. I'm actually not sure what I did here. I think I'm just stop here. I think this is enough for one episode. You can explore all of this on your own. The code is all inside the repository that I mentioned at the beginning of the show, and you can run this yourself in live view and play around with anything you want to play around with. If you have questions about anything I did, please post a message in YouTube chat room in the comments, and I'll try to reply. Thank you for coming to this episode of ElixirZone.